All right, hello everyone, and thanks for attending today's CGD seminar. Before we get started, I'll remind everyone of our CGD Code of Conduct, where we offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. I'll also ask that everyone please keep themselves muted and hold any questions until the end. If you have a clarification question that you'd like me to pass along to the speaker, you can enter that in the chat. Now, it is my pleasure to introduce today's speaker. Clara Desser is Senior Scientist and Head of the Climate Analysis section in CGD. She received a Bachelor's in Earth and Planetary Sciences from MIT and a PhD in Atmospheric Sciences from the University of Washington. Her research interests and expertise include climate change and observations and models, including with interactions across Earth system components on regional and global scales. She's been the recipient of many awards, including as a fellow of AMS, AGU, and last year's National Academy of Sciences. Her talk title today is Projected Changes in Unforced Modes of Atmospheric Circulation Variability over the North Pacific in a Coupled Model Large Ensemble. So Clara, feel free to share your screen and take it away.
Okay, thank you so much, Dan, and everyone for joining. I lost my voice yesterday after being on an airplane, so if I sound hoarse, maybe Dan can play some of his nice music and we can go from there. Anyway, thanks again for joining. I'd like to share with you some work that was led by former postdoc J.P. O'Brien, who was here for a couple of years and unfortunately wasn't available to give the seminar today. So I'm stepping in, but this is very much led by J.P. So we're going to talk about projected changes in unforced modes of atmospheric circulation variability in the CSM1 large ensemble. We have a paper that just got favorable reviews in Journal of Climate, so we're in the process of revising that now. It's posted on my website. Very happy to get feedback on that. So as we know, anthropogenic emissions are influencing our climate now and will do so in the foreseeable future. And the primary radiatively active gases of interest are, of course, well-mixed greenhouse gases, sulfate aerosols, and other components of, from human activities. So these anthropogenic emissions, of course, cause climate change, anthropogenic climate change. And really I'd like to distinguish between these two components of forced change. One are changes to the mean state of the Earth system, and the other is changes to the intrinsic variability within the Earth's climate system. Typically, we expect that as the mean state changes, we may get changes in variability and modes of variability as a result of those mean state changes. And there's the possibility also that the changes in variability can have a rectified effect if there are nonlinearities, and they can have a rectified effect on the mean state. So I think of these two components of force change as going hand in hand. So really, I would say the majority of work done in our community to date really has focused on how the mean state of the climate changes under anthropogenic emissions. This is sort of the typical IPCC reports, very well studied. I think we know a lot about it. But low-hanging fruit, in my view, is examining force changes in variability. And I would say this is an emerging focus. It's definitely more challenging. It requires a lot more samples of variability to really assess whether there are significant forced changes in variability. So when I say variability, you can think in your mind of ENSO as maybe a primary, mode of internal variability in the climate system. So just very broad brush, briefly, my look at the literature on past work on examining force changes in variability. We know from many, many studies and also from theoretical considerations that precipitation is expected to, variability is expected to increase under anthropogenic climate change over a broad range of timescales, daily to decadal. I just point you to this nice paper of Angie Pendergrass that summarizes a lot of the work. Air temperature, I think it's been demonstrated that as Arctic sea ice continues to melt, that it has an impact on air temperature variability at high latitudes, especially over northern Eurasia and Canada. And this is, I think, a well-established mechanism for this decrease in variability. ENSO has been examined, of course, and I would say that the consensus with the current generation of climate models is the expectation that there will be an increase in variance in tropical Pacific SSTs associated with ENSO, but there's large model dependence in the timing and the amplitude of these changes. And a recent study suggests that this actually may change sign when we go to high resolution ocean models, and maybe this expectation is actually reversed with the high resolution modeling. So there's quite a bit of uncertainty in how ENSO may change its character in the future. And then finally, the topic of today is the atmospheric circulation, the large-scale circulation. And I know I'm not comprehensive here in my listing of topics or subtopics or papers, but this is what I could glean from the literature. And I would say that along with changes in ENSO variance, there have been many studies indicating that teleconnections from ENSO will also change in their strength and maybe in their location. Recent work has shown that the North Atlantic Oscillation may increase its variability in the future. And then a nice review paper led by Rob Wills indicates robust decrease in subseasonal meridional wind variability at mid-latitudes. So I would say to date, a lot of this work has sort of been piecemeal, and I think we're poised now as a community to look at this question of changes in large-scale patterns of atmospheric circulation variability in a much more general framework. So that's what we have started down this path, JP and I, and there's lots more to do. So I'll just show you where we have gotten to. in this first paper. But as I say, I think it opens up a lot of interesting questions and avenues for future work. So today our focus is on a general view of the large-scale atmospheric circulation over the North Pacific in winter. So we're looking at internal variability in the wintertime over this region. And we'll address two overarching questions. The first, how will anthropogenic emissions affect the leading modes of internal variability of the North Pacific atmospheric circulation and associated impacts on precipitation? And then secondly, how large are these projected changes in variability compared to those in the mean state? Do we care? Do they matter very much? And our approach, which I will describe in some detail, will be to apply a novel so-called snapshot empirical orthogonal function analysis technique. And we'll apply this to the CESM1 large ensemble over the time period 1920 to 2100. And I'll explain what this approach is in a moment. So here's our study region. We decided to focus in, at least for this first paper, on the North Pacific. You're looking down on the Pacific here. You can see our the red area outlines the region of interest. And we were particularly, we thought this would be an interesting region because it's really a nexus, if you will, for at least two different influences. One is just intrinsic mid-latitude atmospheric dynamics that cause changes in the jet stream, stationary waves, and large-scale patterns of variability. And then, of course, this region is also subject to teleconnections from ENSO. So we thought it might be a particularly rich region to examine. So we'll be using 500 hectopascal geopotential height as our measure of atmospheric circulation. We're going to be looking at DJF, December through February averages for each year. So we're looking at variability from one winter to the next. And we're going to be using an EOF approach. And we're actually going to look at EOFs 1 through 3. Typically, I only look at the first mode because you worry about orthogonality constraints. But in this case, I think that we have good reason actually to go all the way down to EOF 3, as I'll show you in a moment. So the first thing I want to do before I get into this artificial model world is to show you that the model actually in present day actually looks really good. And I think it's a starting point anyway for examining this question. So the first thing I want to just show you is a kind of validation of the CESM1 modes of variability of this 500 hectopascal geopotential height field. So I'll show you the three leading EOFs over this time period from 1958 to 2015. We're using the 20th century reanalysis for this analysis. We've detrended the data, and then we also look at all 40 members of the CESM1 large ensemble, also linearly detrending just to do apples-to-apples comparison. And I just want to mention that EOFs, we may think of them as, of course, they are by definition a statistical technique and maybe an artifact, but actually there's lots of work done on modes of variability in this region. And in particular, this paper by Yuan et al. In 2016, using self-organizing maps, obtains very much the same modes as I'll show you here. So I do think there's a lot of physical basis for these EOFs. So just very briefly, just to show you that, you know, this model has some realism. Here I'm showing sorry, I just have to move these bars so I can see my slides. Okay, here we go. So here we're looking at the first mode. You're looking down on the North Pole, and the North Pacific is in the lower half of the map. So this is EOF1 of so-called Pacific North American pattern, PNA, very familiar. The top map is for the 20th century reanalysis, and the bottom map is stringing all 40 members of the large ensemble together. They both explain about a third of the variance over this domain. And I think you'd agree that there's a lot of similarity between these two patterns. EOF2, whoops. Here we go. EOF2 is looks like this. And again, the reanalysis and the model really over the North Pacific and North America look really similar. And this is the so-called North Pacific oscillation, and also has some aspects of the West Pacific pattern. Many papers, again, have described these modes. And then finally, EOF3 is a less well-known mode. In fact, I wasn't too sure about it myself, but this turns out from the literature to be well documented as the East Pacific pattern, EPP. And here you can see that there's a little bit more of a difference between the model and the reanalysis, although there's some overall similarity over the North Pacific. But just to show you that, we're comparing one realization of in observations with 40 realizations from the model. I can also look at each individual ensemble member in the model. And here's one member that I picked just by eye as having a better match to the observations. So again, the point here is that these modes of variability are well simulated at present day by the model, at least according to this analysis. So I think there's a reason to proceed with the model and look at how things may change in the future. Okay, so that brings me to our crystal ball here, which in this case, we're going to use the CSM1 large ensemble project. I'm sure just about everybody is very familiar with this setup. I think it's a perfect test bed, actually, for looking at this question of how anthropogenic emissions may force changes in both the mean state and the variability. And really, to look at forced changes in variability, you need lots of ensemble members. So it's really the beauty of large ensembles to bring them to bear on this question. So just very briefly outlining the experimental design, there was a long pre-industrial control simulation with the coupled model, fully coupled model. And then in year 401, we applied this hammer, which is the radiative forcing, both in the historical period and the future under the RCP 8.5 scenario, and that was run to 2100. And then on the 1st of January 1920, we introduced a tiny perturbation to the atmospheric temperatures on the order of 10 to the minus 14 degrees Kelvin, which is round-off error in the atmospheric temperatures. And we ran another 39 simulations, so a total of 40. And I'm calling this the butterfly effect. This serves to create spread across the ensemble, and that spread is entirely due to internal variability by design and therefore irreducible. And it is, in this model, largely unpredictable beyond about a few years, although there are some regions associated with slow changes in ocean circulation that may have some predictability out to about a decade. But for the time period that we're looking at, 1930 to 2100, I would say there's very little memory from the initial condition. Okay, so that's the setup of the large ensemble. Now I just want to illustrate for you how we're going to look at internal variability in this large ensemble. So I'm going to illustrate this with just simple time series. This is the so-called Niño 3-4 SST time series in the equatorial Pacific. Haven't done anything to the data. These are just DJF averages for each year from 1920 to 2100 in ensemble member number 1. So this time series then is comprised of intrinsic variability in ENSO plus background climate change. And then if we superimpose ensemble member number 2 and its Niño 3-4 SST record, you can see that it has the same warming trend in the future as the first one. So that's that background climate change. But of course, the sequence of El Nino and La Nina and neutral years need not match between the ensemble members. They have different sequences of internal variability. And number 3 here, just to make the point, drive the point home again, that the individual ups and downs indicative of ENSO events can occur in different years in different ensemble members, or they can coincide, and that's entirely random. What is not random is that background climate change. So the way that we deal with removing this background climate change is to simply remove or take the average of all 40 members at each time step and then subtract that average. And you hope that with 40 members, you have a reasonable number to beat down the noise from sampling variability, and you're really getting at that forced response. So if I do that subtraction, so now we have no background climate change, and we're just left with variability. And you can see that that overall warming trend has gone away, but we've retained all of the ups and downs from ENSO variability. But the important point here is that we haven't removed all forced change in this record, because there can still remain forced changes in the characteristics of this internal ENSO variability. So ENSO can have a change in amplitude in the future under anthropogenic emissions. It can change its spatial pattern, and it can change its remote linkages with other parts of the globe. And these are things that can be affected by anthropogenic climate change. And that's exactly the question that we want to address and isolate with this approach. Okay, so our question at hand is, do the characteristics of the internal variability change with climate change? So traditional EOF analysis is actually not well suited to answering this question. And that's because you perform traditional EOF analysis in the time domain. And so you're getting a spatial pattern of your EOF that is static in time. It doesn't vary over the time period you're applying the EOF analysis to. So that is, not going to help us answer this question. And I think a really great tool for analyzing or addressing this question with large ensembles is to actually turn your head 90 degrees and apply EOF analysis not across time, but across ensemble member at any given time. And this has become to be known as the Snapshot EOF analysis approach, or alternatively, the ensemble EOF analysis approach. I like Snapshot just because it reminds my brain that we're just looking at EOFs at a single instant in time across ensemble members. There's lots of really nice papers that have begun to really use this technique, and I think it's just a great tool for addressing this question with large ensembles. So here the spatial patterns can evolve. And the reason why you can actually do this is, say, look at that red arrow, say that's the year 1960. If you look at the ENSO variability in 1960 in each ensemble member, as we saw just a moment ago, that gives you a random sampling of the internal variability at that particular time. So El Nino and La Nina events can occur randomly between the different ensemble members. So if you have enough ensemble members, you're really getting a lot of samples of ENSO at that given instant in time or given year in time. So again, just to make sure we're all on the same page, here I'm going back to showing you that ENSO SST time series, but instead of showing it to you for all time steps, I've just picked out the values for 1960, and I'm showing you in the vertical dimension here, axis, the ensemble member. So ensemble member 1 at the bottom actually is in a very strong El Nino state plus 2 degrees C anomaly, whereas ensemble member looks like 37 is in a strong La Nina state. So we're getting a really nice sampling of 40 different ENSO states in 1960. So you do your EOF analysis in that dimension, and you can obtain the statistics of ENSO in that time step. So then you apply this snapshot EOF at each year or each time step, and so you do this for all time steps between 1920 and 2100. And what we've a twist that we've applied on this approach is actually to consider actually augment our sample size even more by considering all samples within a 5-year window of the indicated year to get added robustness. So we're not taking a 5-year average because that would average out ENSO. We're simply pooling all of the years from 1958, 59, 60, 1961, and 62, those 5 years. We have 40 samples from each of them. So we have 200 samples for the year centered on 1960 for this 5-year window. And a 5-year window is very reasonable in this case because we are looking at we don't anticipate that the internal variability changes very much over a 5-year window. Okay, so I hope that has explained briefly in a nutshell what the snapshot EOF approach is. It provides a very direct, incisive way to assess the evolving force changes in the leading patterns of internal variability. Okay, so now I'm on to my results, and we'll just get started. So the first thing we often get asked when I've given this talk before is how much variance do these snapshot EOFs explain as a function of time? So let me just walk you through this diagram. For now, you can just pay attention to the red curve, and that's simply showing you the total variance of the geopotential height variability after subtracting the ensemble mean at each time step. So it's the internal variability as a function of time. And you can see that that red curve starts to increase markedly in the second half of the 21st century. And in fact, the total variance increases by something like 35% by the time you get to the end of the 21st century. So that's a big increase in the total amount of variance in the internal variability of the 500 geopotential height field over the North Pacific domain. Then you can ask, how much variance does each of these EOFs explain as a function of time? So here I'm just labeling those 3 EOFs for you and their curves. And then the cyan colored curve is the sum of the variances of each of these three modes. And by and large, you can see that the explained variance remains relatively constant, although the total variance that these are explaining does increase with time. So that's just a sort of a background on these EOF variances look like. Okay, now the fun part is to look at the patterns themselves. So this is the regression map of the 500 millibar height field onto the standardized snapshot principal component. And the domain for the EOF analysis, as I indicated, is in this red box. So that's the North Pacific. We standardize the associated PC, and then we regress all the grid points onto that PC. And remember, the PC is a function of an ensemble member, so we can do this regression at each time step. So this map is showing you the pattern that we get in 1920. And this is what I mentioned earlier, the Pacific North American pattern. The stippling or the dots show the values that are significant at the 99% confidence level. And here we're showing you the positive phase of this mode for convenience, but this is a linear analysis, so the negative phase is implicit. So this is our familiar P&A pattern. Now I'll show you how this pattern evolves in time by showing you this nice animation of this first mode as a function of time. And you can keep your eye on the years within this green box to see where we are. So now I'll let that animation run. Now we're in the 1930s, 1940s, 1950s, 1960s, 70s, 1980s, 1990s, the 2000s, 2010s, 2020, 2030, 2050. You can start to see some market changes compared to 1920. Now we're in the 2070s, 2080s, 2090s, and finally at the end here, 2100. So this pattern, because of this snapshot approach, we can really see that it has changed character over time due to anthropogenic forcing. So a notable feature, of course, is the deepening of the Aleutian low. It's off of our color scale by the time we get to 2100. And then you can also see that the connection to the North Atlantic has become a lot stronger in 2100 than in 1920. And the amplitudes throughout the tropics and even into the southern hemisphere in the Pacific have also amplified with time. So now I'd like to move on to the impacts of this mode on precipitation. So here are the snapshot EOFs for this first mode, just summarizing the beginning of the record, 1920, and the end of the record, 2100. So these are regressions on that first principal component. And now the contours are the 500 millibar height field that you saw a moment ago. And the shading is now the precipitation regression pattern. And the stippling is on the precipitation. And what you can see here are, as expected, if the circulation variability intensifies with time, so do the associated precipitation changes. And just to summarize, what we see is in the future that this mode intensifies and the precipitation impacts over California, the southeastern part of the US and Europe, and certainly the tropics increases with time. We see this expanded spatial footprint across the North Atlantic in the future and the strengthened linkage to precipitation in the tropics. So this mode, the take-home message is that this mode is not static. It is influenced by anthropogenic emissions, and we have to pay attention to it. So now I'd like to move on to a summary of the first three modes. I'm going to skip the animations for time constraints, and I'll just summarize for you each of the three modes. And I'll show you again this contours for the 500 hectopascal height field and precipitation in the color shading. So this is mode one. It's a slightly different projection than what you saw a moment ago, but it's showing you for the global domain north of 30 degrees south. The maps on the left are showing you what this mode looks like in 1920. The maps in the middle are for 2100 at the end of the simulation. And the maps on the right are showing you the linear trend across all time steps between 1920 and 2100. So we have this snapshot EOF for each time step, and we can simply at each grid box compute the linear trend in those regression maps, and showing you here that these trends are highly significant at almost all grid boxes over this domain. So there are significant trends, as you saw a moment ago, in the PNA pattern. And just to point out a couple of features, in the Pacific, you can see the PNA is associated with enhanced precipitation variability in the tropics and enhanced circulation or elution low variability over the North Pacific. And it's associated with sort of an NAO-like circulation pattern in the Atlantic sector. So here's mode two. You haven't seen that before for the future. So this is all from the model. This is this North Pacific oscillation or West Pacific pattern. And you can look at 1920 and 2100. The changes in the circulation are not that pronounced in the Pacific sector, but there is an increase in the linkage with precipitation in the tropical Pacific, and there's an increase in the linkage with the NAO. So this mode, even though it doesn't change its character all that much in the North Pacific, it has a stronger linkage to the North Atlantic and to the tropical precipitation in the future. And finally, mode three, this is this East Pacific pattern, which again, I was not going to pay attention to until JP said, look, we have to pay attention, because this mode of all three modes actually shows the largest forced changes in the future. And that was a surprise. I don't pretend to understand why, but it's obviously very important, and we need to understand the dynamics of these changes. So just to summarize, all three modes show enhanced linkages to the North Atlantic in the future and to the tropical Indo-Pacific precipitation variability in the future. And surprisingly, this East Pacific pattern, mode three, shows the largest circulation changes of all three modes. Okay, so an obvious question to ask now is, given these marked changes in the tropical precipitation linkage, how much do forced trends in ENSO variability contribute to the forced trends in the extratropical variability that we're seeing in these modes? So the way we're going to address this is by looking at the two leading modes of tropical Pacific SST. And I'm not going to show you those modes per se. We've applied the Snapshot EOF approach to the tropical Pacific SST field after removing the ensemble mean, so just the internal variability. And what I'll show you are the regression maps of the 500 hectopascal height field and precipitation onto those PCs. Based on the tropical Pacific. So our snapshot EOF domain is in this red box. So that's the tropical Pacific. And you're seeing the associated regressions of precipitation in color shading and 500 millibar heights in the contours. So this is for the Snapshot EOF in 1920. It explains 55% of the SST variance in that red box. So it's obviously a dominant mode. It's the canonical E-specific ENSO mode, although I haven't shown it to you here. What happens in 2100? Here's that same first mode in 2100. Now it explains just slightly more of the variance, but you can see it is greatly enhanced, both in the precipitation field in the tropics with an eastward extension into the far eastern tropical Pacific, and an enhancement of the geopotential height field, both over the North Pacific and over the North Atlantic. So future enhancement of this E-specific flavor, if you will, of ENSO variability and its associated teleconnections to the North Pacific and to the North Atlantic. And then I'd like to show you mode 2. And this mode also shows future enhancements, primarily over the Pacific sector for circulation and for precipitation. And you can think of this mode as perhaps reflecting the Central Pacific flavor of ENSO, although it may also reflect asymmetries between El Nino and La Nina in the first mode. And I think both of those interpretations probably have merit, and that's something that we are currently looking into as we revise our paper. So what we're going to do is we're going to take these two modes, and we are going to, I'm just going to skip this for the interest of time, and we're going to parse the forced changes in the internal variability in the 500 millibar height field using those two tropical modes. So to be specific here, what we do is we take those two leading snapshot principal components that you just saw of the tropical Pacific SST variability at each time step. We regress those PCs from the 500 millibar height field globally. So we remove their linear influence, if you will, from the 500 millibar height field. And then we take that residual 500 millibar height field that has no tropical SST influence, and then reapply our snapshot EOF analysis to that residual field. So that's how we're getting a handle on how anthropogenic emissions in the absence of changes in the tropics may influence the extratropical atmospheric circulation, i.e. via mid-latitude atmospheric dynamics. And then to assess the role of the tropical influence, we simply take the snapshot EOFs from the total height field and subtract the snapshot EOFs from this where the tropical influence has been removed. And that's how we assess the contribution of this indirect pathway or tropically mediated pathway of the changes. So just to be clear, anthropogenic emissions can affect the character of ENSO variability in the tropics, and that then can change the characteristics of the tropically induced teleconnections to the extratropics. And then there can also be a role for intrinsic mid-latitude atmospheric dynamics in how anthropogenic emissions can affect these modes of variability. Okay, so I hope that was sufficiently clear. So I'm going to summarize for you then these two pathways of influence. So I'll do this by showing you the trend maps of these snapshot EOFs. So these are these linear trends of the EOFs at each time step from 1920 to 2100. This is for mode 1, the PNA. And on the left is the map you've seen before. That's the total height field, after removing the ensemble mean. So that's what you saw before, an enhancement of circulation variability, not only in the North Pacific, but also in the North Atlantic and associated enhanced variability in the tropical Indo-Pacific. So then we parse this or decompose this into these two influences. The tropical influence from these leading two modes of SST variability in the tropical Pacific, and the, quote, no tropical influence after removing those modes from the 500 millibar height field. And it's a little hard to see, maybe because of the contour interval, but I think you can see if you focus on the number of contours in the North Pacific and the North Atlantic, that both pathways are actually have roughly the same magnitude of influence and contribute roughly the same magnitude to the total forced change in this mode. The patterns are somewhat different, which speaks to different processes. One is tropically induced teleconnections, and one are, intrinsic mid-latitude dynamics. But these patterns, the magnitude of the patterns are quite similar. Of course, as expected, the tropical influence shows the tropical precipitation variability. And when we remove that from in the no tropical influence map, we have almost nothing left in terms of tropical precipitation influence. So I think we have taken out the bulk of the tropical influence with these first two modes. So now we'll look at the second mode, this North Pacific oscillation / West Pacific pattern. And here, again, both pathways contribute. The North Atlantic oscillation, it looks a little different in the pattern and where that nodal line sits. But again, the magnitudes are very similar for these two different contributions. And again, there's very little tropical influence left in the precipitation field in this middle map. And then finally, this East Pacific pattern, which was the most interesting because it showed the largest trends in the future. And here, the distinction between how the tropical influence, the pattern from the tropical influence and the no tropical influence, their patterns are almost orthogonal, and they're extremely well-organized patterns, and they are very different. And I'm very excited to probe the dynamics that gives rise to these two different pathways. Okay, so now I come to the last part, and I only have two more slides to show, and then I will wrap up and take questions. So as I posed at the outset, we had two questions. So now we're on to the second one, and I've decomposed that into two parts. So the first part is, how large are the projected forced changes in the characteristics of the internal variability compared to the forced changes in the mean state? So using this old-fashioned balance to connote, what is the relative amplitudes of these forced changes in mean state and variability. So here are the results summarized here. So let me walk you through the slide. So the top map is something you haven't seen before, but it's what's in the IPCC reports and so many papers that have gone into those reports. So this is simply the mean state trends. So linear trends in the mean DJF 500 millibar height field and precipitation from 1920 to 2100. So the way that we get the mean state is to average all 40 members of the ensemble at each time step. That gives us a good handle on the forced response. And then we simply fit a linear trend to the data at each grid box. So you can see enhanced circulation mean state deepening of the low pressure systems in both the North Pacific and the North Atlantic, some projection onto the North Atlantic oscillation, and also an enhancement of precipitation mean precipitation in the equatorial oceans. Then in the red box here are the trends in these internal modes of variability. So you've seen these before. These are the trends in those snapshot EOFs for each mode. So you've seen all the results before. But what's new here is that we're putting them on the same footing as the ensemble mean trends. So the contour intervals are identical and the precipitation color bar is identical. And what you can see is if you pay attention to the circulation field, the contours, and think about superimposing these different modes, they're kind of same order of magnitude. The mean state trends still dominate, but I would argue, especially in the Pacific and parts of the North Atlantic, that you cannot ignore force changes in the internal modes. The maximum amplitude of the trends in the internal modes are of similar magnitude in parts of the North Pacific and especially in the North Atlantic west of Europe there. Precipitation is definitely dominated by the mean state trends. But again, take-home message, we can't ignore trends in the internal modes when we look at force trends that they can superimpose on the force trends in the mean state. So a slightly different question is to ask is, do force changes in the mean state dominate over internal variability that exists in 2100? So it's not quite the same question as we looked at a moment ago. Here we're just asking, we know there are mean state changes. We also know there's internal variability superimposed on those mean state changes. How large are they relative to one another? So the top map is going to look very familiar. It is simply showing, just with different units, the mean state change. So we've simply taken the mean state in 2100, actually the last decade of the simulation, the 2090s, minus the first decade of the simulation, so the 1920s, and simply form the epoch difference between those, the 40-member ensemble mean. So except for the units, the pattern is indistinguishable from the trend map that you saw a moment ago. And then in the red box, we're showing the modes of variability from the snapshot approach in 2100, so in the future. And this is their one sigma, one standard deviation amplitude of their PCs. So if you think of them as being normally distributed, 2 sigma level would encompass minus 2 sigma to plus 2 sigma would encompass the 5th to 95th percentile range that one would expect for the amplitude of these modes. So if you think of doubling the contour interval in the red box and doubling the precipitation shading of the maps in the red box, you can very easily see that internal variability can overwhelm the forced response, even in 2100. This is nothing new. This has been a message from early on with large ensembles that you have to be aware of this range of outcomes in the future due to the superposition of the internal variability in the mean state. Okay, so now I will wrap up with a summary and open questions. And just to remind you, we've been looking at the 2 components of forced change, how anthropogenic emissions can influence the climate system. One is through changes in the mean state. And again, I've argued that's been very well studied by now. But another that is low-hanging fruit that I think really is the second layer of the onion, if you will, that we're peeling, is to look at how anthropogenic climate change can affect the character of internal variability. And probably the internal variability is very much responding to changes in the mean state, but it could potentially have some rectified effect on forced changes in the mean state. Perhaps ENSO is a good example, but that needs more fleshing out to really see if that's the case. And our toolkit here has been the CSM1 large ensemble and the snapshot EOF analysis approach, which I think is just a perfect way or a very incisive, direct way to look at these questions with a large ensemble. So we have three summary take-home messages. The first is the leading modes of wintertime North Pacific atmospheric circulation variability in the CSM1 large ensemble intensify, they expand into the North Atlantic and show enhanced linkages to ENSO in the future. And surprisingly, the third mode, the East Pacific pattern, is the one that shows the largest changes under anthropogenic climate change. Secondly, it's clear from these results that both tropical teleconnections and intrinsic mid-latitude atmospheric dynamics both play a role in these forced changes in the internal variability. And thirdly, future changes in the variability are the same order of magnitude as those in the mean state and can overwhelm the mean forced response even in 2100. So we really have to pay attention to potential forced changes in variability when we make our projections. So future work, open questions. Of course, how realistic are these projected changes in the CSM1 large ensemble? And very importantly, what are their underlying mechanisms? What is the model dependence of these results? And are there any emergent constraints that can be brought to bear on these results? I have no answers to any of these, but this is future work, and I hope this will be undertaken by many of you, and I'm excited to see that going forward. So on my plate anyway, next steps in the near future will be to apply a similar analysis to other model large ensembles, other regions of the globe, and seasons. And we'll start out with this multi-model large ensemble archive that the US CLIBAR Working Group on Large Ensembles has assembled. And then next step in the near term, I think, is to implement this snapshot EOF analysis approach in the climate variability diagnostics package for large ensembles. I just think it's the right tool for large ensembles to look at how these intrinsic modes of variability may change under climate change. And with that, I thank you very much, and I welcome questions. Thank you.
Great. Thank you so much, Clara. We have time for one or two questions. Dylan, go ahead.
Hi, Clara. Great talk. I appreciate you going through all of that. Just a quick question. I'm wondering if the changes that you see in these atmospheric modes correspond to changes in related SST modes that respond strongly to these patterns, like the PDO in response to the first mode or the Pacific Meridional mode in response to the second mode. I'm just wondering if the internal changes that you're seeing project also onto the popular SST modes in the North Pacific.
Thanks, Dylan. Great question. The answer is yes. I didn't show it, but we have the regression maps of SSTs for each of these atmospheric modes. And sure enough, as you're guessing, you do get the imprint of the modes in terms of the PDO and the NPO related SST patterns. So the answer is yes.
Awesome. Thank you.
All right. Nicola?
Hi, Clara. Great talk. I was wondering whether you'd thought about splitting your trend period up into kind of shorter periods to see whether the trend's consistent across the whole time period or if it's at the end or anything like that.
Great question, Nicola, and I know why you're asking it, and I think it's an awesome idea to do that. And if I may say that a few words, Nicola has just done a really nice analysis of how ENSO and others of how ENSO changes in the future in all these different model large ensembles. And it's very clear that the timing of the intensification of ENSO is model dependent. And in some models, it happens in mid-century, and then there isn't much change after that time. And some models, it doesn't happen till the end. So I'm expecting that, yes, it will be model dependent. And I think it'll be a really nice way to compare models once we parse these forced changes into the ENSO contribution and into the non-tropical contribution. And I agree that should be done as a function of time. So thank you very much for that question.
Okay, and one last quick question from Rob, 30 seconds.
Hi, Clara. Thanks for the clear and interesting talk. I was wondering if these EOFs in each of the analyses you've done, if they always show up with the same number, you didn't have to do any reordering or anything to keep them consistent. And if that's the case, that's in some sense a surprising result in how robust these patterns are, even to large changes in climate. I was just wondering if you could comment on that. And also if are these three EOFs for the North Pacific, are they well separated from the fourth?
Well, thank you, Rob. So the answers to both questions are yes. So the first is that these are robust. I think it's partly because we have pooled all 5 years together. So we have 200 samples. So EOFs 1 and 2 look almost the same, at each time step. EOF 3 might change a little bit. And I do think that that is a reflection of, that it explains less variance, but you can still identify it, but the centers of action may move around a little bit. All 3 modes are well separated from one another and from the 4th mode at each time step, and we have verified that from the North et al. Criterion.
Excellent. Well, let's thank our speaker again, and thanks everyone for attending. We'll look forward to seeing you next week. Take care.
Thank you.